Let's see Kepler's laws. First law is law of orbits. What is law of orbits? According to this law, all the planets they move in elliptical orbits around Sun with Sun at one of the foci. Now, what is an ellipse first? Let's go into that. You all know that equation of a circle with center at origin, if radius is r, is given by x square plus y square equals to r square. What is x and y? They are coordinates of any point which lies on the circle. What does it mean? It means that distance of any point from the center is always what? R. What is an ellipse? If you stretch a circle in an oval form like this, then this thing is called an ellipse. In the ellipse, we define two things. One is major axis and the other one is minor axis. If there is a point x comma y on the ellipse and you take this intersection of major axis and minor axis as origin, then if length of half of the major axis, which is called semi-major axis, is A, and that of half of the minor axis, which is called semi-minor axis, is B, then equation of an ellipse is given by x square upon a square plus y square upon b square equals to 1. If you say that A and B, they both are same, then it becomes a circle like this. A circle is a spatial ellipse where your semi-major axis and semi-minor axis, they both are of same length. Now, A and B, they are related like this. B square is A square times 1 minus E square. This E is called eccentricity. And its value is root over, you can see from this, move E square this side and then take the root, you get 1 minus B square upon A square. For an ellipse, your E must be less than 1 and greater than 0. Your eccentricity should be less than 1 and greater than what? 0. For a circle, E becomes what? Look here. For a circle, you know that B and A, they both are same. If they both are same, then this is 1 minus 1 and you get E as what? 0. Circle, which is a special case of ellipse, you can say that for that eccentricity is what? 0. Eccentricity you can understand this way, how odd this side is with respect to this side. For a circle, they both are same and therefore you say that there is no E, or E becomes what? 0. Now, this E gives you the position of focus. For an ellipse, there are 2 points which you call focus. This, let's call it F1, another one here, F2. This distance from the origin is AE. AE and AE. So if somebody asks you the coordinates of this point, then you will simply say that since this length is AE, coordinates of this point are minus of AE, which is the x coordinate, and y coordinate is what? 0. Similarly, you can find coordinates of this point. Coordinates of this point are AE, comma 0. Now, for the first law, we say that all the planets, they move in elliptical orbits with Sun at one of the foci. That means if Sun is present here or is present here, then a planet will move like this. So if we draw path of all the planets, it will look like this. This is Sun. If you say that this is the path of Mercury, then let's say this is the path of Earth. They both are ellipse with Sun present at the one of these two, which is, let's say, F1 in this case on the left side. So this Sun, its position is the focus of the ellipse. Now, all the planets, if you draw path of Jupiter, Neptune, Pluto, anything, you will find that Sun is present at the focus of all these elliptical trajectories. This is the first law. Each and every planet, it moves in elliptical orbit about Sun. And it's not about Sun and the planet. If you say, what is the path of Moon around Earth, then that is also what? Elliptical, with Earth present at the focus. So in this example, if you say this is Earth, then this will be the path of Moon. Any satellite which we launch is most of the time in the elliptical orbit, and these elliptical orbits, they are always going to follow this law with Earth present at one of the focus. Note down this much regarding law of orbits, but first write down the statement. Write down this also in the form of statement. All the planets revolve in elliptical orbits. All the planets revolve in elliptical orbits about Sun, with Sun present at one of the foci. With Sun present at one of the foci. Next line. This statement is true. This statement is true for any body revolving around Earth. This statement is true for any body revolving around Earth. For example, if we consider Moon, then path of Moon is also an ellipse with Earth present at with Earth present at one of the foci. If you remember, time and again you will find these kind of news that Moon is closest to Earth. So when you say Moon is closest to Earth, had it been a perfect circle, Earth present here and Moon orbiting in a circular path, then all the time distance of Moon from Earth will be what? Same. But that's not the case. Moon is moving in an elliptical orbit. So if Earth is present here, Moon, if it's present at this position, that will be the closest position. This closest position of any body about this focus is called perigee. Closest point. The farthest point from the focus, this point, it is called apogee. So, if Moon is present here and Earth is present here, then you will see the largest size of Moon. And when it moves to the other side, at the apogee, definitely size will reduce. So that's how all these planets, they move about Sun. They follow these elliptical trajectories. Note down this much. Kepler's second law is law of areas. First write down the statement and then we'll see what basically it is. Radial vector from Sun to any planet sweeps equal area in equal time. Sweeps equal area in equal time. What is radial vector? Suppose Earth is present at this point. If Earth is present at this point and is moving in this direction with velocity v, then after some time Earth will be present at this point. Started from this point, after some time you found that Earth is present at this point, then this is the radial vector from Sun to Earth. It sweeps this much area. Let's say Earth moves from this point to this point in time dt. In time dt. If the area covered is dA, area swept by the radial vector is dA, then second law says that dA upon dt, which is also called aerial velocity, is constant. Now what is happening? When Earth arrives at this position, and if you take same time interval dt, then in this time interval dt, Earth will cover this much area. It may seem that this area is larger, but no. Look at this height. This height is less as compared to this. And therefore, when Earth moves from this position to this position in time dt, then you will find that this area is also what dA. This area is what dA, this area is also what dA. Which means you can see that as a planet comes closer to Sun, it has to travel a larger distance. Then only you can have equal area. And that's why we say that according to the second law, as a planet comes closer to Sun, its velocity increases. Write down this statement. As a planet comes closer to Sun, to have same aerial velocity, its speed should increase. Its speed should increase. That means if I ask you, what is the point where velocity of a planet will be maximum, then you will say that when a planet is at perigee, if its velocity is vp, and when a planet is at apogee, its velocity is va, then this va is minimum. This vp is maximum. So when a planet is at perigee, closest point from the Sun, velocity is what? Maximum. When a planet is at apogee, farthest point from Sun, its velocity is what? Minimum. We can also find this dA by dt with the help of angular momentum. Now we will find that dA by dt. Look here. In this elliptical diagram, if we find the area dA covered in dt time, then it will be something like this. This is Sun. This is some planet. It's moving in this direction. Its velocity is what? V. Let's say it was present at this position at time t, and it arrives at this position at t plus dt, when time is t plus dt. That means it moves from this point to this point in time dt. When it moves from this point to this point in time dt, let's say the distance of the planet from Sun is r, and the area swept by the radial vector is this. If this is the area, then if I say that this height or this perpendicular which you draw on the velocity vector is h, then area of the triangle which you see dA will be what? Half of base and the height, product of base and height. What is the base? It's moving with what? V. In what time it moves from this position to this position dt, and therefore base length is nothing but V multiplied by dt. That's your base multiplied by h. Half of V dt base into height. That's the area represented by the blue shade in this figure. Now, what is aerial velocity? dA by dt. So what is dA by dt? dA by dt is coming V into H divided by 2. V into H divided by 2. Now let's multiply M, which is the mass of the planet in the numerator as well as the denominator, and it becomes mvh divided by 2m. Now what is mvh? From rotational motion you know that what is mvh. If this is the axis of rotation and this is the velocity, then this is what? Linear momentum mv. This is your linear momentum mv. And what is this? Perpendicular distance of linear momentum from the axis of rotation. In this direction, you see what? P, which is linear momentum, that is m into v. And this linear momentum, its perpendicular distance from the axis of rotation, which is present at Sun, is h, and therefore this mvh is nothing but L, which is what? Angular momentum divided by 2m. So dA by dt is coming what? L divided by 2m. Now we can prove that this L remains constant. This angular momentum, it remains constant. Then we can prove that aerial velocity is also what? Constant. Now, how can you prove that L is constant? What is that which changes L? Torque. Now, this is Sun, this is the planet. Sun is pulling on this planet towards itself with the gravitational force of gm1m2 upon r square. The important point is that this gravitational force which is acting on the planet always passes from the Sun. Now, what is Sun? Sun is also axis of rotation. So, gravitational force, as it passes from the axis of rotation, its torque is what? 0. And when torque is 0, you know that angular momentum will remain what? Conserved. L is constant, m is mass of planet, that is also constant, and that gives us a constant aerial velocity. Note down this and write down the statement. Kepler's second law is based on conservation of angular momentum. Kepler's second law is based on conservation of angular momentum. Next line. As gravitational force of Sun on any planet, gravitational force of Sun on any planet passes from the Sun itself, its torque will be zero. And therefore angular momentum remains conserved. Now, note down this much and then find out ratio of Vp and Va. You need to find Vp and Va in terms of distance of perigee from Sun and distance of apogee from Sun. Let's say distance of apogee from Sun is RA and distance of perigee from Sun is RP. Then in terms of RP and RA, you need to find VP and VA. Put on this much, pause the video, and then go for VP and VA, ratio of these two things. If you cannot, come back and see the solution. So, when you say that angular momentum remains conserved, let's find out angular momentum when planet is at perigee. Find out angular momentum when planet is at apogee, and then these two things should be what? Same. So the argument is that angular momentum at perigee is same as that at apogee. What is angular momentum? Linear momentum multiplied by perpendicular distance from the axis of rotation. This is the axis of rotation. This is linear momentum, and that's the perpendicular distance. It's this much easy. So what is LA? Linear momentum m into VA multiplied by perpendicular distance, which is RA. Same is the case with angular momentum at perigee. Your axis of rotation, this is what? Linear momentum. When a planet is at perigee or when it is at apogee, the thing is that this angle is always 90. So when this angle is 90, we can directly find perpendicular distance. Perpendicular distance you can see is this RP. And therefore, at perigee, your angular momentum is coming m into VP multiplied by RP. The aim is to find what? VP upon VA. You can see that VP upon VA is coming RA divided by RP. RA divided by RP. Now, we can also relate RA and RP in terms of semi-major axis A and eccentricity E. RA and RP. Try to convert these things in terms of A and E. For an ellipse, this is the origin, this is the focus, and this distance is what? AE. This is AE, and half of semi-major axis is what? A. This half is also what? A. When a planet is at perigee, its distance from the focus is what? From this to this, it's what? A. This is AE, and therefore distance from focus to perigee is what? A minus AE. This RA becomes A minus AE divided by RP. Sorry, what is RA? RA is A plus AE. When you go for distance of apogee, you can see that this is A and this is AE, and therefore numerator is what? A plus AE, and denominator is A minus AE. That gives us VP upon VA. This VP upon VA is coming 1 plus E divided by 1 minus E. 1 plus E divided by 1 minus E. For a circular orbit, what is E? 0. You can see that becomes what? 1 upon 1. For a circular orbit, your VP and VA, they both will be what? Same. Note down everything. Now Kepler's third law is law of periods. It simply says when a planet, let's say Earth, it moves in the elliptical path, then time it takes to complete one revolution around Sun. This time period, which for Earth you know is 365 days, this T is proportional to square of T. Square of T is proportional to cube of semi-major axis. T square is proportional to A cube. This is origin. This distance is A. This is Sun at the focus. Time to complete one rotation about Sun, which a planet takes, is square is proportional to what? A cube. For elliptical orbits, mathematically it will take a lot of time to develop this thing. We have done a proof of this thing for circular orbits with the help of Newton's laws. If you remember, for a circular orbit where radius is r, in the article of orbital velocity, we had found v, and with the help of v, we found t, and that t was coming proportional to r cube. Now, what is a circle? A circle is a special case of an ellipse. If it's a special case of an ellipse, then you can see that semi-major axis is what? R. Semi-major axis is what? R. And therefore, this law, which is valid for elliptical orbits, can be directly used for a circular orbit also in this form. We have already seen proof of this. Its proof is mathematically difficult. Now, how come it's difficult? We'll solve a simple example in the next part, and that will give you an idea that to develop this thing will take good maths. Note down this, and then we'll solve a few questions on this part. Note down the question. We have the ellipse. Sun is present at this point. This is apogee. At apogee, velocity is VA. At perigee, velocity is VP. Our aim is to find VA and VP. At every point, speed is changing continuously. Farthest you are from Sun, your velocity is least. And then it increases, becomes maximum at perigee. And then again, as you move away from it, velocity decreases. We need to find this VP and VA. Pause the video, think about it, how we can find VP and VA with everything which we have learned so far. If you cannot, come back, take the hint, and then again pause the video and try to find it. So, our aim is to find VP and VA. That means there are two unknowns. And for two unknowns, we must have two equations. First equation we got from COAM. That was also Kepler's second law, conservation of angular momentum. And that conservation of angular momentum says that Vp upon Va is 1 plus E divided by 1 minus E. This is the first equation, which is coming from COAM. If you can write second equation, then question is done. Again, pause the video, think about the second equation, how do you arrive at that, and then solve these two equations. For second equation, we will be using COME, conservation of mechanical energy. On the system of Sun and the planet, there are no external forces. Sun is pulling the planet, planet is also pulling the Sun. There are no external forces, and if there are no external forces, no external work is being done. No external work is being done. And therefore, we can use what? Conservation of mechanical energy. For COAM, torque was 0. On the revolving planet, torque coming from gravitational force is not present, and therefore we could use COAM. On the system of Sun and the planet, there is no external force, and therefore we'll be using COME. Let's say mass of Sun is m and mass of the planet is m. This distance is Rp, this distance is Ra, Rp and Ra. So what is kinetic energy at perigee? Half m Vp square. What is potential energy at perigee? Minus of Gmm divided by Rp. This is total mechanical energy at perigee, which is equal to total mechanical energy at apogee, and at apogee this energy is half m V A square minus of Gmm divided by Ra. This is your equation number 2. You got kinetic energy at perigee, potential energy at perigee of the system of Sun and the planet. Same mechanical energy is present not at apogee, everywhere. At this point, at this point, at this point, everywhere your angular momentum is what? Same, conserved. At the same time, your total mechanical energy is also what? Conserved. Solve these two equations and you will get the answer. The value of Rp, this Rp is A minus AE, and this Ra is A plus AE. When you put these values, you will get Vp. It's very easy to solve these equations. Now find out Vp in terms of Va and then put that Vp in this equation and you will get Va and Vp both. After solving, you will get your Vp as root over Gm divided by A 1 plus E divided by 1 minus E. An important result for competitive examinations. What is velocity at perigee? Root over Gm by A 1 plus E upon 1 minus E. What is velocity at apogee? Root over Gm by A 1 minus E upon 1 plus e. At times, people commit silly mistake like these: 1 minus e and 1 plus e. So remember, when you are at perigee, your velocity is what? Maximum. So this number, this thing should be greater than what? VA. And therefore, in perigee, numerator is what? 1 plus e. Velocity at apogee, numerator is what? 1 minus e. Take the ratio of these two, it's coming 1 plus e upon 1 minus e. First check. Second check. For a circular orbit, if you remember, orbital velocity was root over gm by r, where r was what? Radius of the orbit. For a circular orbit, your e is what? 0. This is gone. 1 upon 1. For a circular orbit, your a is what? R. And therefore, Vp is coming root over gm by r. Because of this, since v changes, it becomes difficult to calculate time. It was much easier for a circular orbit, because in a circular orbit, throughout your speed is what? Constant. And we could use time as what? Distance divided by speed for circular orbit. For elliptical orbit, distance divided by speed is not valid, because speed is not constant. Note down this much. Now look at effect of Earth's rotation about its own axis on strength of gravitational field G at the surface. This is Earth. This is Earth's axis, which is passing from north and south pole. And about this axis, Earth is rotating with angular velocity omega. So Earth is rotating about the north and south axis, and you know what omega is. Omega is 2 pi upon t. Earth, it takes time t to complete one rotation, and this t, you know, is not 365. This is 24 hours. This is 24 into 3600 radians per second. This is your equator. If somebody is present at this point, then if no rotation is present, mass of Earth is m, any point present on the surface, its mass is m, Earth is pulling this m towards itself with a force of F. This F is G m divided by r square on the surface. Since you are present on the surface, you can consider all of its mass at the center. So this force G upon r square is something which you call mg naught. From this we get g naught as gm divided by r square. So if Earth is not rotating like this, then somebody is going to feel this much gravitational acceleration, gm upon r square, which is directed toward the center of Earth. But because of this rotation, what happens? At this point, the thing which is present at this point is also completing a circle like this, a smaller circle. As you approach North Pole, radius of this circle will become what? 0. Right now, let's say you are present at this point. Somebody who is present at this point is a non-inertial observer. What is a non-inertial observer? It's coming from pseudo force. An observer who has some acceleration is called what? Non-inertial observer. Now, since Earth is rotating with angular velocity omega, anything which rotates with omega must have centripetal acceleration, and therefore, let's say you are standing at this point. If you are standing at this point, then as an observer, you are a non-inertial observer. And non-inertial observer, to convert himself into an inertial observer, he must apply a pseudo force. If you remember direction of that pseudo force, that direction of pseudo force is this. This is your pseudo force. Direction of pseudo force is away from the direction of, is in the opposite direction of acceleration present. This is a circular path. For a circular path, you need centripetal acceleration. That centripetal acceleration is acting towards this center, not this. For this person, this is the circular path. Now, for this circular path, this is your centripetal acceleration, and for this centripetal acceleration, because of this centripetal acceleration, this man is a non-inertial man, non-inertial observer. To convert himself into an inertial observer, he is using pseudo force. What's the strength of pseudo force? Pseudo force is mass of the object multiplied by acceleration of non-inertial observer. So on himself, he is applying this much pseudo force. What is A? A is nothing but centripetal acceleration present at this point. What is centripetal acceleration? R omega square. Every point on the surface, on this earth, will have what? Same angular velocity. It doesn't matter if you are present here, anywhere you are present, your angular velocity will be what? Same. Velocity will be different, and therefore we are not using v square upon r. We are interested in what? R omega square. This pseudo force is nothing but centrifugal force. What is the centrifugal force? When you rotate in a circle, you feel an outward force, a force which you feel acting on your body away from the center. That force is nothing but centrifugal force. What is the centrifugal force? A pseudo force. So this pseudo force I mean is mr omega square. At the same time, in this direction, towards the center of Earth is present m g naught, this f. So somebody present on the surface of Earth is going to experience these two forces, mg naught and pseudo force mr omega square. Resultant of these two will act somewhere in this direction. This F total is called mg, and this is the g which you feel right now. If I drop this marker, then this marker is moving not in the direction of mg naught, but in the direction of F total. And therefore, if you drop this marker and somehow you allow it to move through the earth, then it will not reach the center. It will deviate and move in the direction of F total. Because of what? This pseudo force which is present on the body. This mg is g effective, which we are interested in. So when I say effect of Earth's rotation on g, we are interested in the actual g which you feel. If you stop Earth from rotating, you're going to feel g naught. Now, if this point which we have taken on the surface of Earth, if you take this point in this form, from the equator, this point is at an angular position of theta. From the equator, if you are at this point theta, then gravitational field G at this point is given by G naught minus R omega square cos square theta. Not a difficult task. You have got two forces, F1 and F2. How do you find F total? Root over F1 square plus F2 square plus 2F1 F2 cos theta. You need to find angle between these two forces, which you can easily find because this angle theta is given. Solve that F total, and this F total is what? mg. After simplification, you arrive at this. Remember the direct result. If somebody is interested, go for that F total formula and you will reach at this point with a few approximations. Why? Because look at the omega part. This omega is a small number. And you are also using what? Omega square. So when you simplify things, you will be eliminating few terms and ultimately you will arrive at G equals to G naught minus R omega square cos square theta. Somebody interested, go for it. Otherwise, for everyone, it's a result. Theta must be taken from the equatorial line. That means, if you look at this formula, what is the G at equator? For equator, your theta is what? 0, and therefore G at equator cos theta 0. What is cos 0? 1 is coming G naught minus R omega square. This is G at equator, which is also minimum of G present on the surface of Earth. On the surface of the Earth, if you are present anywhere on the equator, you will experience minimum G. When you go and reach poles, somebody at poles, for poles your theta becomes what? 90. For poles theta is what? 90. What is cos 90? 0. And your G at poles is simply what? G naught, which is the maximum value of gravitational acceleration. On the surface, if you are at North Pole or South Pole, you will experience maximum G. If you are on the equator, G will be least minimum. G naught minus R omega square. You can understand it in this form. When you are at the North Pole, at the North Pole, this circle is almost gone because you are itself on the axis. If you are on the axis itself, if you are standing on the axis itself, that means you can say that the circle you are describing is not present. If you are not describing any circle, that means there is no centripetal force. If there is no centripetal force, whatever you experience is what? mg naught. So if you drop something at North Pole, and if you allow somehow to pass through Earth, then it will definitely pass from the center of Earth. But if you drop it from this point, it will not move in this direction because of the presence of this pseudo force. It will move like this. Hopefully you understand the effect of Earth's rotation on G. Note down this much.